Welcome to G Fun Facts Online. Today we are diving into a massive technological revolution happening quietly behind the scenes of our digital lives. When you think of the modern internet, you might picture invisible wireless signals or endless lines of software code, but the physical reality of our connected world has a very distinct sound. It is not the sound of traffic or the chatter of crowds. It is the low, steady, deafening drone of cooling fans inside massive data centers. For 50 years, this sound has been the literal heartbeat of our digital civilization, a necessary byproduct of keeping the silicon brains of our servers from melting down under their own computational weight. But we are now standing on the precipice of a brand new era. Generative artificial intelligence, high-performance computing, and our insatiable global demand for massive amounts of data have pushed this traditional cooling method to its absolute physical and economic limits. That familiar hum is becoming a roar, and more importantly, it is becoming a massive liability. To understand why we are on the verge of a cooling revolution, we first have to appreciate the fundamental failure of air. Since the dawn of the data center industry, the premise has been brutally simple: condition the air in a massive room to keep the servers cool. This ecosystem relies on gargantuan chillers, computer room air conditioning units, raised floors, and complex hot and cold aisle containment systems. It is an entire architecture built around moving vast, hurricane-like volumes of air just to strip heat away from tiny blistering hot pieces of silicon. But physics is not on our side here. Air is a terrible conductor of heat, its thermal conductivity is incredibly low, and its capacity to hold heat energy is severely limited. As chip manufacturers like NVIDIA, AMD, and Intel push the boundaries of physics, packing more and more transistors onto chips at the microscopic atomic scale, the thermal density is skyrocketing. We are now seeing the thermal design power, or TDP, of a single computer chip pushing past 400 watts, 700 watts, and even rocketing toward 1000 watts. To cool these incredibly dense components with air requires an airflow so massive and violent that it creates acoustic issues capable of physically vibrating and destroying nearby hard drives. Furthermore, the electrical energy required just to spin these screaming fans can easily consume 20% or more of a server's entire power budget. The industry has hit a hard thermal wall. In a standard air-cooled server rack, you can typically manage about 15 to 20 kilowatts of total power before you create dangerous hotspots that threaten to crash the hardware. If you want to cool a 100 kilowatt artificial intelligence cluster with air, you are forced to physically space out the racks. This wastes incredibly valuable real estate inside the building and increases the physical length of the fiber optic cabling between servers, which introduces latency and slows down the entire network. Air cooling is officially bottlenecking the future of human computing. The solution to this thermal crisis requires a fundamental shift in physics. We have to move away from a gas medium and embrace a liquid medium. Liquid is approximately 1,200 times more effective at removing heat than air. This is a foundational fact of thermodynamics that makes liquid cooling not just a fun alternative, but an absolute inevitability for high-density computing. Now, water is the most efficient common coolant on the planet. But water is highly conductive and corrosive. If a single drop of water touches a running motherboard, it causes an instant short circuit and catastrophic failure. Because of this, traditional liquid cooling uses a method called direct-to-chip. This involves pumping water through elaborate networks of pipes into metal cold plates that sit directly on top of the processors, keeping the water safely separated from the sensitive silicon. While effective, direct-to-chip cooling only targets the hottest components, leaving the rest of the motherboard reliant on those same old, noisy fans. This is exactly where immersion cooling enters the picture, a technology that sounds straight out of science fiction, but is rapidly becoming the gold standard for next-generation digital infrastructure. Instead of piping water to the chips, immersion cooling submerges the entire electronic assembly into baths of specialized dielectric fluids. These are engineered liquids that absolutely do not conduct electricity. Because they are completely electrically insulating, you can safely take a fully operational server, including the motherboard, the central processing unit, the graphics processing unit, the memory sticks, the power supply, and all the cabling, and dunk it directly into the liquid bath. This creates a thermal environment of unparalleled efficiency. Every single millimeter of every component is in direct, intimate contact with the coolant. There are absolutely no hotspots, because the fluid effortlessly fills every microscopic nook and cranny. Those massive, bulky metal heat sinks that are required for air cooling are completely removed. They are replaced by the natural thermal mass of the surrounding fluid. The screaming fans are permanently removed. Suddenly, the data center transforms from a deafening, windswept warehouse into a completely silent, incredibly dense, and thermally rock-solid environment. As this technology matures, the world of immersion cooling has naturally divided into two primary schools of thought, each with its own specific mechanics, benefits, and champions. These are known as single-phase and two-phase immersion cooling. Let us break down exactly how they work. In a single-phase immersion system, the dielectric fluid stays in a liquid state throughout the entire cooling cycle. It never reaches a boil. The servers are lowered vertically into a specialized tank, which looks somewhat like a high-tech chest freezer, filled with a hydrocarbon-based fluid. This fluid is often similar to highly refined mineral oil or advanced synthetic variations. As the electronic components operate and generate intense heat, they warm the fluid directly surrounding them. This warm fluid naturally rises to the top of the tank through convection, or it is gently pumped out to ensure optimal flow. It then flows through a critical piece of equipment called a coolant distribution unit, or CDU. The CDU acts as a massive heat exchanger, taking the heat from the hot dielectric fluid and transferring it into a completely separate water loop connected to the facility's main cooling system. The newly chilled dielectric fluid is then pumped back into the server tank to repeat the continuous cycle. The fluids used in single-phase systems are viscous, slightly oily substances with extremely high boiling points, making them excellent at absorbing and retaining heat. The major pros of single-phase immersion are that it is mechanically simpler, easier to contain because you are not dealing with expanding vapors, and the fluids themselves are generally cheaper and last for many years without degrading. It is also exceptionally quiet and requires less daily maintenance. However, dealing with dripping, oil-soaked servers can be messy for technicians during repairs, and it is slightly less efficient at removing extreme, sudden heat spikes compared to our next method. This brings us to two-phase immersion cooling, which is widely considered the absolute high-performance sports car of the cooling world. Two-phase cooling offers vastly higher performance, but comes with higher costs and significant mechanical complexity. In a two-phase system, the servers are submerged in a specially engineered fluorochemical fluid that has a remarkably low boiling point, often right around 50 degrees Celsius, or 122 degrees Fahrenheit. This is where the magic happens. When the high-performance chips heat up and hit that 50-degree mark, the fluid literally begins to boil directly on the surface of the silicon. This phase change, the rapid transition from a liquid to a gas, absorbs a truly massive amount of energy. In thermodynamics, this is known as the latent heat of vaporization. The fluid boils, turning into a vapor that quickly rises to the completely sealed top of the tank. There, the vapor hits a series of cold condenser coils that are chilled by facility water. Upon contact with the cold coils, the vapor instantly condenses back into a liquid state and rains back down into the primary bath, ready to absorb more heat. Historically, these two-phase fluids have been incredibly thin, completely non-oily, and evaporate instantly upon exposure to air, meaning when you pull a server out, it is completely bone dry in seconds. The heat rejection capability of two-phase cooling is utterly unmatched. It can effortlessly handle extreme chip densities, easily cooling racks, generating 100 kilowatts or more. Furthermore, the violent bubbling action of the boiling fluid creates microscopic turbulence that physically scrubs the heat away from the chip surface. However, there are massive drawbacks. These highly engineered fluids are staggeringly expensive, often costing hundreds of dollars for a single gallon. The tanks must be perfectly hermetically sealed to prevent the expensive gas from leaking out and being lost forever. And most crucially, we are currently facing a massive environmental and regulatory reckoning regarding the chemicals used in these fluids. This brings us to a critical turning point in the history of immersion cooling, a monumental shift known as the Great Fluid Transition. For years, the undisputed king of two-phase immersion cooling fluids was a product line called Novec, manufactured by the 3M Corporation. It was a miracle fluid. It was non-flammable, non-toxic, and incredibly thermally efficient. But Novec, along with many similar fluorinated compounds, belongs to a family of chemicals known as per- and polyfluoroalkyl substances, widely referred to as PFAS, or forever chemicals. These chemicals do not readily break down in the environment, leading to severe ecological and health concerns globally. In late 2022, 3M made a shockwave announcement that they would permanently cease manufacturing all PFAS products by the end of 2025. The industry standard was suddenly on the chopping block. While this announcement caused immediate panic, it has also spurred an incredible, rapid wave of chemical innovation. The entire data center industry is now pivoting aggressively towards sustainable, PFAS-free alternatives. For single-phase systems, the market is incredibly robust and evolving beautifully. Major petrochemical giants have stepped up to the plate. Companies like Shell, with their gas-to-liquid synthetic fluid, Castrol with their ON product line, and ExxonMobil have all developed highly refined synthetic oils that offer phenomenal thermal properties without the lasting environmental baggage. But perhaps the most fascinating development is the rise of bio-based fluids. Cargill, a massive global food and agriculture corporation, has introduced a breakthrough product called NatureCool. This is a highly advanced dielectric fluid derived directly from vegetable oils, specifically soybeans. It is over 90% renewable, fully biodegradable within a matter of weeks, and entirely carbon neutral because the plants absorb carbon dioxide while they grow. This plant-based fluid has a flash point of over 300 degrees Celsius, making it incredibly fire-safe. For massive hyperscale computing companies with aggressive corporate sustainability goals, pouring highly engineered vegetable oil on their servers is suddenly the most attractive option on the market. For two-phase applications, the challenge is much harder. Chemical companies are desperately searching for drop-in replacements that mimic the exact boiling properties of Novec, but without persisting in the environment for millennia. Heavyweights like Chemours and Honeywell are currently developing hydrofluorolefins, or HFOs. These next-generation chemical compounds are designed to provide the same high-performance boiling phase change, but they are chemically engineered to break down in the atmosphere in a matter of days rather than thousands of years, offering a regulatory-compliant path forward for extreme density computing. While the chemistry and physics are fascinating, the true test of any technology is its application in the real world. Over the past few years, several major players have moved immersion cooling far beyond the proof-of-concept phase and into massive, full-scale production, acting as true pioneers of the deep. Let us look at Alibaba Cloud. Facing the absolutely staggering computational demands of China's booming digital economy, Alibaba deployed their proprietary InnoChill single-phase immersion cooling technology at scale. In their massive Hangzhou data center, they achieved a power usage effectiveness, or PUE, of 1.05. For context, a perfect PUE where exactly zero energy is wasted on cooling is 1.0. Reaching 1.05 is a stunning engineering achievement. By completely eliminating server fans and giant air conditioning units, they reported total energy savings of 45% compared to their traditional data centers. This is not a small, isolated experiment in a lab. It is a massive hyperscale deployment definitively proving that single-phase immersion can support colossal artificial intelligence and big data workloads with ultimate reliability. Then we have Microsoft. Their journey into alternative cooling famously began with Project Natick, where they literally sank an entire sealed data center off the rugged coast of Scotland. Through that wild experiment, they discovered that a stable temperature environment filled with inert nitrogen gas significantly reduced hardware failure rates. Taking those lessons back onto dry land, Microsoft built a facility in Quincy, Washington, becoming the first major cloud provider to run a full production two-phase immersion cooling system. They discovered a fascinating side benefit. Because the boiling fluid created such an impossibly stable thermal environment, they were actually able to safely overclock their servers. They could run the processors significantly faster than the manufacturer's rated speeds without any risk of overheating, effectively extracting free extra computational power out of the exact same silicon. Another incredible example is Wyoming Hyperscale White Box. In a bold and visionary move, they designed a massive facility from the absolute ground up to be completely free of air cooling. Partnering with Submerge, a leading manufacturer of immersion tanks, they are utilizing single-phase immersion to cool racks of unbelievable density. But the real genius of Wyoming Hyperscale is what they do with the heat afterward. In a traditional data center, waste heat is blown out into the atmosphere as 35 degrees Celsius air, which is basically useless low-grade heat. But the waste heat captured by an immersion fluid can easily reach up to 60 degrees Celsius. This hot liquid is incredibly easy to transport through closed pipes. Wyoming Hyperscale is taking this hot fluid and using it to provide central heating for a massive, adjacent indoor vertical farming operation. This brilliant industrial symbiosis turns the data center from a massive waste generator into a vital heat provider, perfectly closing the sustainability loop. Finally, long before artificial intelligence took the global spotlight, the cryptocurrency mining industry was the original driver of extreme high-density cooling. Companies like Bitfury, through their acquisition of Allied Control, deployed absolutely massive 40-megawatt two-phase immersion cooling mines in the Republic of Georgia. These rugged facilities proved that you could run highly specialized chips at intense densities of up to 250 kilowatts per single rack, all in warm climates without paying a single dime for massive air conditioning chillers. They proved to the world that immersion cooling could unshackle data centers from cold climates, allowing them to be built anywhere on Earth, regardless of local temperatures or water scarcity. And water scarcity is a massive point here. Traditional air-cooled data centers consume millions upon millions of gallons of fresh water every single month, just to run their evaporative cooling towers. Because immersion cooling relies on a sealed, closed-loop system, that hot return water can be cooled by simple outdoor radiators, even in the dead of summer. This singular technology can reduce a data center's water consumption by up to 100%, a metric that is becoming absolutely critical as local municipalities push back against tech giants draining their local reservoirs. But adopting this technology dramatically alters the daily operational reality of a data center. The life of a technician changes overnight. You can no longer simply walk down a cold aisle, open a metal rack door, and hot swap a broken hard drive in 30 seconds. When you walk into an immersion data center, instead of towering vertical racks, you see endless rows of horizontal tanks that look exactly like industrial chest freezers. Servicing a server requires physically hooking it and lifting it vertically out of the fluid bath. In single-phase systems, that server is going to be dripping wet with highly refined oil. Technicians must use specialized service rails to hang the server above the tank, allowing the fluid to drip back down for a minute or two. While modern synthetic and soy-based fluids are completely non-toxic and safe to touch, they are incredibly slippery. The floors must be kept pristine, and fixing components requires specialized stainless steel prep tables and ultrasonic degreasing baths. You also have to consider material compatibility. You cannot just dunk any cheap plastic cable into hot oil. Over a few years, warm dielectric fluid will chemically extract the plasticizers out of standard PVC cable jackets, making the cables brittle and contaminating the expensive oil. Standard thermal paste will simply wash away, requiring specialized indium foil or solid polymer thermal interfaces. Even standard paper barcode labels will dissolve into mush, meaning servers must be laser etched or tagged with specific polymer labels. Because lifting heavy, slippery servers out of deep tanks is ergonomically dangerous and difficult for human workers, immersion cooling is rapidly driving the massive adoption of robotic maintenance. We are seeing the introduction of integrated, automated gantry cranes and highly precise robotic arms that run along tracks above the tanks. These robots can lift massive servers, place them into dedicated service cradles, or even precisely swap out modular components without human intervention. This entirely eliminates the risk of human injury and drastically reduces the chance of accidentally dropping a slippery, $40,000 artificial intelligence server back into the tank. For years, a severe lack of standardization heavily restricted the broader adoption of immersion cooling. Every tank vendor had entirely different dimensions, different fluid specifications, and totally different warranty policies. Plunging a traditional server into a tank of oil used to instantly void the manufacturer's warranty. But this Wild West era is rapidly coming to an end, largely driven by the Open Compute Project, or OCP. The OCP's dedicated immersion cooling project has released incredibly detailed guidelines that have quickly become the global industry Bible. They have standardized material compatibility lists, defined exact tank dimensions so servers can be freely moved between different vendors, and pushed for rigorous safety testing. The Global Safety Standard, UL 62368-1, Edition 4, now includes very specific, rigorous annexes purely for liquid-filled electronic components, mandating strict tests for fluid overflow displacement, extreme pressure buildup, and flammability. Thanks to these standardization efforts, major original equipment manufacturers like Dell, Hewlett-Packard Enterprise, and Supermicro now offer servers specifically engineered, tested, and fully warrantied from the factory for immersion cooling. They arrive on loading docks completely stripped of those useless fans and bulky air shrouds, ready to be dunked on day one. As we look toward the horizon of 2030, the trajectory of human computing infrastructure is abundantly clear. The absolute explosion of generative AI is creating server racks that demand 100 kilowatts of power or more. Physics dictates that air simply cannot handle this density. We are witnessing a massive, permanent bifurcation in the global market. Standard business applications and lightweight web hosting will likely remain on legacy air-cooled infrastructure for some time. But the massive, sprawling brains of the internet, the giant clusters training massive large language models, the supercomputers running complex scientific simulations, and the dedicated hardware driving high-frequency financial trading will move almost exclusively to advanced liquid cooling, with immersion absolutely dominating the extreme high-density market. Because of this, we will soon see the rise of dark data centers. These will be massive, lights-out facilities completely devoid of human technicians. Designed strictly for endless rows of immersion tanks and automated robotic servicing, they will be optimized purely for absolute thermal and computational efficiency rather than human occupancy. We will also see a massive expansion of energy reuse. Taking a cue from Wyoming hyperscale, major utility companies in Europe are already pioneering this. In Helsinki, Finland, Microsoft, and the local utility company Fortum are building a massive system where the high-grade waste heat from new immersion data centers will provide an astonishing 40% of the entire district heating needs for the neighboring cities of Espoo and Kauniainen. The hot water generated by the computing power is pumped directly into massive heat pumps, boosted slightly, and sent flowing into the city's vast underground pipe network to keep thousands of residential homes warm through the brutal Finnish winter. They are literally turning the digital cloud into physical warmth for human beings, transforming data centers into massive, zero-emission digital boilers. Immersion cooling is no longer a fringe, niche experiment reserved for cryptocurrency miners hiding in cold warehouses. It is the absolute necessary evolution of the entire data center industry. It is the critical, foundational technology that will allow humanity to continue endlessly scaling our massive digital ambitions without physically cooking the planet in the process. The deafening hurricane hum of the cooling fans is finally fading away, being replaced by the silent, absolute efficiency of the fluid bath. The thermal crisis is ending. The age of immersion has officially arrived. Thank you for tuning in to G Fun Facts Online. We will see you in the next deep dive into the technology shaping our future.